All right, today we're going to be dealing with uniform circular motion. Uniform meaning constant speed. So the first question is something that we dealt with earlier in the year. Is an object moving in a circle accelerating? Well, we know the answer is yes, because remember, acceleration is a change in velocity, and velocity is a vector. So as an object moves in a circle, its velocity is changing direction, which means that velocity is changing, right? So therefore it has an acceleration. The direction of the acceleration is always toward the middle of the circular path. Now, how do we find that acceleration? Well, that's a little bit tricky because the magnitude of our velocity is remaining the same. So let's figure out what's going on here. We've got a circle. Okay. Say we've got velocity vector, or v initial, and then a short time later, v final. These have the same magnitude. Yeah. If we take our circle, we have one radius, two radius, those are the same radii. Now some time interval passes as the object moves between those 2 points. Now as we take the limit, as that time interval goes to 0, now this arc basically becomes a chord. Okay, so we've got that arc at the edge of the circle. Well, as these vectors get close, as this time interval gets smaller and smaller and smaller, these 2 points get closer and closer together, right? And as they're like here, when they're really close together, if we were to say here and here, when they're really close together, that arc isn't much different from the chord, which is the straight line that connects those 2 points. And when we approach that limit, well, then we can say, okay, we got radius, radius, chord, all right? And these velocity vectors, being tangent to the circle, are both perpendicular to the radii. And because of that, we can say, if we put those velocity vectors into a triangle, v initial, v final, we know that angle is the same. We know that these two sides are the same, and these two sides are the same length, which means the other two angles are the same as well, which means we have a similar triangle. And when we have an initial and final velocity vector, the vector that connects those two is the change in velocity. So then we have similar triangles. When we have similar triangles, we can write a proportion. We can say that C over R is the same thing as delta V over the magnitude of either one of these, which we can just call V. Okay. Now, the length of this chord, we've got an object moving at speed V over time interval t, and it's moving at constant speed, so we can say that the length of the chord is just that speed times time, and then we can plug that in, so that's vt over r equals delta v over v. Moving that around a little bit gives us v squared over r equals delta v over t, and delta v over t we know is just acceleration. So that's our formula, that the acceleration, and it's called centripetal acceleration of an object moving around in a circle at constant speed is equal to v squared over r. That's the formula we're going to be using. Oh, I have it here. Since distance is velocity times time, if we take a full circle, we can say velocity is distance over time, and for a full circle, that's a distance of 2 pi r. And the time it takes for one full circle is also known as the period, which is written as capital T. So that's an expression for velocity. So we can also say that centripetal acceleration is 4 pi squared r over period squared. That's an alternate version of the formula. This is not on the formula sheet. The other one, I believe, is. Yeah. So acceleration is caused by a force. We know this, by a net force. When the total acceleration is toward the center of the circular path, that means the total force is pointing toward the center of the circular path. We call that a centripetal force. Now, keep in mind, it is a net force that causes an acceleration. So centripetal force is the net force acting on an object moving in a circle. Okay? The net force. So it goes on, if you write net sigma F equals ma, the centripetal force goes as the total over here. Or sorry, not the total over here. Sorry, this total is equal to the centripetal force. So the mass times centripetal acceleration goes on the right side. Centripetal force goes on the right side. I don't know why I wrote the left side. Sorry, that's a... It goes on the right side. The acceleration, you're plugging in v squared over r for acceleration. And the reason that I'm making a point of that is that when you're doing one of these problems, say you have gravity, normal, whatever, that are all contributing to the acceleration of the object moving in a circle. On the left side, you would put normal plus gravity plus whatever, adding up all the forces that are acting. And on the right side, you put mv squared over r. Okay. On the left side, you do not put gravitational force plus normal force plus centripetal force. It's not an additional kind of force. It's a descriptive term for the sum of all the forces. All right. So just keep that in mind. So we'll see what that looks like as we work through some problems here. For each of these, let's just think about what forces are acting and which ones actually contribute to the centripetal force or the centripetal acceleration. And when I say contribute, I mean either adding to or subtracting from. So either pointing toward or away from the center of the circle. So we've got a mass on a string moving in a horizontal circle. Forces that are acting are going to be tension and gravity. And if the circle's horizontal, gravity is going to be perpendicular to that circle, so that won't contribute to the centripetal, but the tension will be pulling the mass toward the center of the circle, so that would contribute. If we've got a vertical circle, same deal. We still have tension. We still have gravity. Gravity is going to go down, tension is going to go up. So for the circle's vertical, both of those will contribute mostly, except for at these two particular points when the mass is straight to the side, then they'll be perpendicular. But at most times they'll, the tension will always contribute, but at most times gravity will contribute as well, except for those two specific points. If we've got a car driving around a curve on a flat road, well, we have gravity, normal, and friction going on. Well, gravity and normal are going to be up, and if they're on a flat road, the curve is going to be, the circle would be in a horizontal plane. So friction is the thing that would be pulling the car into the circular path. A banked curve is one where the road is moving in a circle, but it's also at an angle. It's like the car is on this angle and then also going around in a circle. Yeah, it might be hard to picture on a 2D paper, but if you Google it, you can probably find a better picture. Like racetracks are kind of like this, where around the curves the road is not only turning, but it's also tilted toward the center. So on a banked curve, we have the same three forces acting. But because the road is tilted, the normal force then would have a component pointing toward the center, and friction also. If the car drives over the top of the hill, then we just have gravity and normal force acting. And as we're going over the top of a hill, gravity would be down, normal force would be up, so both of those would contribute. And the point I wanted to make here is that all of the forces that we've learned about so far can contribute to the normal force in certain situations. Right. This question is just getting at a particular point about centripetal acceleration. So if we were running around an oval track at a constant speed, where is his centripetal acceleration the greatest? Well, the equation is v squared over r, right? So if he's going at constant speed, the radius will determine when his centripetal acceleration is the greatest. The key point to get here is that this radius is the radius of curvature. So if we're curving more sharply, that's a smaller radius of curvature. If we're curving more gradually, that's a bigger radius of curvature. It's like how big of a circle is that part of the path? So like if if I was running over here, well, what's my circle? Well, we're curving pretty tightly, so the circle is something like this. Whereas over here, the circle is like this big, giant thing. Right, so over here, radius is smallest. The radius of curvature is the smallest, so the centripetal acceleration is the biggest. Now if we've got this situation, we've got two masses attached to a string, one's at the end and one's halfway down. So we've got one mass here, and we're going around in a circle, right? So what the mass at the end is centripetal acceleration AC. What's the centripetal acceleration of the other mass? Well, these two aren't going to go at the same speed because they're both traveling in a circle in the same amount of time, but the one that's at the end of the string is traveling in a bigger circle, right? So what is the same is the period, the time it takes them to complete one circle. So the equation that is most instructive is the alternate version of the centripetal acceleration formula. So based on this formula, when we have the same period, we can see that centripetal acceleration is proportional to the radius for two objects that have the same period. So the mass at the end is centripetal acceleration AC. The other mass has, if the mass at the end is radius r, one at the end will have radius r over 2, and since they are directly proportional, the acceleration of the other one will be AC over 2. Now in this case, what's the same between the two? Well, the speed is changing, but they're on the same track, so the radius of curvature is the same. And then we want to find the centripetal acceleration. So in this case, since we're seeing the effective velocity, it's v squared over r, so centripetal acceleration is proportional to v squared. So the ratio, well, dog A would have v squared over r. It's a centripetal. Dog B would have 4v squared over r, so 2v squared. So the ratio of A's to B's is going to be 1 to 4. This one here is just a simple application of the formula. We're just going on a circular 1 kilometer track. That's going to be 1,000 meters. We're running 4 laps in 25 minutes. Okay. Well, that means our period, 4 laps in 25 minutes, is 25 over 4, but that's in minutes. We want seconds, so 25 over 4 times 60 means that our period is 375 seconds. So if we've got a period of 375 with a radius of 1,000, 1 kilometer. The track is 1 kilometer long, so then our radius is going to be 1,000 over 2 pi. And so then we can calculate our centripetal acceleration for pi squared r over period squared. And we can multiply that out for pi squared times 1,000 over 2 pi divided by 375 squared. It comes out to 0.0447 meters per second squared. All right.